So let me copy the function. So this is the cube root of x for x less than or equal to -1, x -1 less than x less than or equal to 2, x minus 1 squared for x greater than 2. So this is very important to understand that, as I just put it in the recycling bin, as I said a second ago. So when you click on the lecture notes, you can go to any video from any part, but look what we wrote. I just want to show this because other students may have the same difficulty. So graphing a function, I put all these. So what the difficulty was, right, this is your starting point. So first you have to find the domain, then you have to create a table of ordered pairs, then you have to graph, and then you find the range. This is always true for anything. Is this okay? So that's the starting point. So when we look at this function, I realize that this is nothing else but negative infinity and -1. Is that okay? So yes?
Quick question.
Yes?
Kind of related to it, but not necessarily related to it.
Yes?
So step 2 was making a graph of the ordered pairs or a table of the ordered pairs.
Yes.
Since these are pretty basic parent functions, do we necessarily have to do that, or if we just drew the graph, is that okay? If we
Never.
Include
Never. I can't give credit for that.
Okay.
And I'll explain why. So this is not the final answer. Allow me to show, and once I finish with the table of ordered pairs and everything, I'll explain why I said what I said. I'm the type of person that I like to ask why. Don't just say, try this. Explain to me why, and then I'll think about it and I'll try it, right? So I do the same thing to my students. I would like to explain everything I say and why. And I'm learning from my students. If you come up with an idea that I probably haven't thought of, it's very possible, a lot, right? I will learn from you. So keep that in mind. So I did not answer, I still have to answer your question. So it's not clear cut yet, okay? So I will come back to your answer, to your question, okay? So first we have to find the domain. That's the first step for any function we graph. This one is basically -1, 2 with a bracket, parenthesis, bracket. And this one is 2 to infinity. So now I can establish the fact that this function is defined everywhere. To the left of -1, at -1, to the left of -1, at 2, to the right of 2. So domain of this function is everything. Now I'm in the step that is step number 2, in which I have to present the ordered pairs. And the ordered pairs are based on the fact that this is the domain. So this has to be in the table. That's why I determined it first. Those numbers of -1, 0, and 2. 0 has to be in the table even if the function is not defined there, unless the function is only defined at 2 to infinity. Then I cannot put 0 in. Okay, so now under -1, I have to have this symbol and this symbol. Under 2, I have the bracket and the parenthesis. Notice that if the point does not exist, I will have 2 parentheses and nothing in between. They will not touch. But because on one side there is a bracket, on the other parenthesis, they have to touch. And please do not write them like this. They have to be exactly under -1. Not to the left, not to the right of -1. So this has to be compact, one below the other. Same thing with this. Now I make myself a note. This side is the cube root of x. The middle part is x. The right-hand side is x minus 1 squared. Why do I write this? Because they may not be presented to me in the correct order. A lot of books scramble them. And who knows, I may plug in something in the wrong branch. Okay, so now, again, I will graph with 3 different colors. Why? Do you have to do that? No. I will graph with 3 different colors because I will see it. It will break my heart, but I will see something like this, which is not a function. So you cannot extend this graph to the right of -1. You cannot extend x to the left of -1 or to the right of 2. You cannot extend x minus 1 squared to the left of 2. So I will have 3 colors, red, whatever, and blue. I don't know, turquoise and blue. Okay, so now I always look for the x and y intercepts. Remember, x and y intercepts. If they exist, they may not exist. So with -1, inside the bracket, I write -1. I don't want to put in -2 because -2 will be difficult. I will not be able to plot. Let's say I put in -8. When I plug in -8, I get -2. And I'm done with this side. Now the middle part, I plug in -1 and I write inside a parenthesis -1. 0 is 0 and 2 is 2. Done with the middle. And now the right, when I plug in 2, 2 minus 1 is 1, 1 squared is 1 inside the parenthesis. And I would like to put in 1, but 1 is not here. That's the x-intercept. So I have to put in 3. So 3 minus 1 is 2, 2 squared is 4. The reason why this table is extremely important is from this table, I see that the limit from the left is -1, the limit from the right is -1, the limit from either side is -1. But here, the limit from the left is 2, the limit from the right is 1, so the limit from either side will be
any.
Thank you. So the table is very powerful. I do not take credit for it. I did not invent it. Okay, so step number 3 is the graph. Okay, again, 1, 2, 3, 4, 5, 6, 7, 8, and -2. So this is 1 point right here. -1 is -1 because there is a bracket here. This is a full point. So it's that -1, -1, and this is the graph. Why? Because the graph of the cube root looks like this. So this is the graph of the pure cube root. But I have to stop here because the cube root is only between -infinity and -1. I'm done with this. Now in the middle. This is a linear function. -1, -1 starts here, 0, 0 continues here, and 2, 2 is 2, 2. With a full point. This is a full, this is an open, but it's the same number, so you will not see that. So here it is. Done with the middle, and now with blue, 2, 1, this has to be an open point. This has to be an open point. And then 3, 4. And here's a quadratic function. So this is a quadratic function like this, right? So we know that x minus 1 squared would have looked like this with a vertex at 1. But I can't. I can only graph what I have. So I see the range is between -infinity. Any horizontal line will cross the function at least once. So now I have the range, -infinity to infinity. All this has to be presented as is. So now I'm coming back to the question. Can I just graph it without the table? No, because I won't be able to. Not because I don't want to. I won't be able to. I won't be able to identify the jump. The graphing calculator does not give us the open point and the full point. Yes, you can put this in the graphing calculator. It would be a waste of time. So this was number 4. Yes.
So what I meant was knowing, like if I did like the mental, like, okay, I know I can't do it, but if I did it mentally, I feel like I did come out with the same answer. I realized that there were a few other things that I'd messed up, but like, yeah, I guess the table would help. Never mind.
Not just that, but trust me, later in this course, we're going to add to this table 2 more rows. One will be the first derivative and the other one will be the second derivative, and they will go in sync so perfectly that you will be able to graph a function without a calculator. It will be so powerful information. So that's why I don't ever recommend not showing work, because if you don't show work and the graph is not correct, then I can't give any partial credit. Unfortunately, I can only give a grade on what I see. I can't say, I think the student knows. Let me give her 100%. I have to grade what I see. That's the problem. That's my predicament when I grade. I have to grade what you put in writing. That's the problem here. Good. Enough of that. Anything else? Other questions?
I have a quick question about
Sure.
that same problem.
Yes.
So in that instance, when at the point -1, -1, I know we have both an open point because of the left side of the table.
Yes.
Oh, I mean a closed point because of the left side, and then an
Yes.
open point on the right side.
Yes.
So would the correct way to draw your graph just draw straight through it, or do you want to see like an open point hole there? How would you like to see that?
You cannot show an open point anymore. If it's the same point, you cannot show anything
Because
else.
it's included in the other functions.
You cannot. There is nothing you can do.
Okay.
Yeah.
Thank you.
Thank you. Other questions? Anything else?
So
Yes?
it also asked for number 12. It said determine the values for a for which would be the limit, where the limit exists. So would it be
Sketch the graph of the function, determine the values of a for which the limit from either side exists.
Mhm.
So
would it all sides except for where the jump is?
correct. So the limit as x approaches a of f of x exists except when a is 2.
Okay, thank you.
Thank you. Anything else?
Is that exactly how you'd write the answer to that?
How I would write the answer, I just didn't read the whole thing. I thought it was just a graph. So how I would write the answer is exactly what we just said. The limit from either side exists for all points or x values except x equals 2. Good. Anything else? Was there anything else that you encountered from anything? Okay, then, so we'll continue with 2.3. If you remember something, stop me anytime. So in 2.3, we're going to talk about limit laws. And the limit laws exist only if we make the following assumption. That the limit, there is a long list of limit laws. As x approaches a is a number. It doesn't matter, we denoted it by L. And the limit of g of x as x approaches a from either side is another number called m. So this is our assumption. If those limits don't exist, infinity or D and E, the limit laws cannot be applied. So what are these? So here's one. the limit of a sum of two functions as x approaches a is, and no, we are not distributing the limit operator. We are only saying the limit of a sum equals the sum of the limits. Okay? Now, of course, if we have minus here, we have minus here. So I like to present these two together. Now, I'm not lazy about writing. I'm trying to condense them. In number 2, if we have a limit of a constant times a function, so when we say multiplication, we mean that this is a factor. I'm not talking about plus 5. I'm talking about multiplied by 5 or multiplied by 10. The constant can go in front. So the constant times the limit of f of x as x approaches a. Oh, I forgot to write here, of course, if this is L and this is M, then we have L plus or minus M, of course. This is less important. The idea is that they exist. Of course, here it will be C times L. Okay, number 3, limit law number 3. So the limit of f of x times g of x as x approaches a. Any wild guess? What do you think this will equal to? Anyone?
Limit of f of x as x approaches a times the limit of g of x as x
It was
approaches
an educated guess, actually. Thank you very much. Of course, M times L. Any questions so far? I know we haven't even discussed an example, but if you have any doubts, always stop me. Okay, number 4. Of course, the limit of f of x divided by g of x as x approaches a. Another educated guess from you, from anyone.
Limit of f of x as x approaches a for f of x over the limit of of g of x as x approaches a.
Makes sense. Very good. Of course, this will be L divided by M, but here I did not have a big if, but here I have a big if. What is the big if here?
If the limit of g of x as x approaches a doesn't equal 0.
Absolutely. Thank you very much. That's it. Good. Now let's look at the limit of a constant. Stop me if you have questions. So the limit of a constant as x approaches a. Another educated guess from anyone?
The constant.
Of course. Who cares where x is going? If I have $10 in my pocket and I don't do anything to it, it will not go anywhere, right? Number 6, the limit of f of x would like to any power, raised to any power. This is n. Sorry, my handwriting is not the best, I think. So n and m. So this is my n and this is my m. Sorry about that. Okay, as x approaches a. And n is a positive integer. N positive integer. Okay, so we will learn in this, in the next section, continuity, it's 2.5. So we're going to talk about the fact that this, as we know, is an operator, and this is an operator. It's a power. Anything that I apply to a function, it's an operator. What operator? Power 2, power 3, power so on and so forth. I'm allowed to swap these two, meaning, see, the power touches the function. And after that, I apply the limit. I can swap the order. I can make the limit to touch the function, and then this to be applied last. So right now, the power is applied first, and then the limit operator. But under conditions of continuity, I'm allowed to put in the limit inside and the power outside. So this is the same with limit as x approaches a from f of x, everything to the nth power, which is L raised to nth power. Okay, so this is possible under certain conditions, and the conditions are continuity. Of course, in this particular case, most probably everything is complied with, but this is a theorem. In short, it's called swapping of the order of operators. This is how I like to call it, so then students remember